So let's take a moment and bring together what we're talking about when we have a power series that approximates a function. So we saw in the last section that we can find a Maclaurin series for sine of x. And that Maclaurin series is a polynomial that goes on forever. So it's a series, and it is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th power over 7 factorial, going on forever. And we could write that as a summation. So as a summation, this is negative 1 to the power of n, over, actually I'm going to put this term on top, so times x to the 2n plus 1, because again, those are all of our odd numbers, so all of our exponents are odd numbers, over 2n plus 1 factorial. And that would be starting at n equals 0. So what we are claiming is that this series is equal to this function. So in other words, if we want to know the sine of 1, we know that the sine of 1 is an irrational number, and that's not something that we're going to know from the unit circle. But according to this, if we were to plug in a 1 for x, I know that 1 to any power is just going to be 1. So these two things should be the same. So our series expression should be the same as the sine of 1. So let's take a look at our calculator and figure out if this is actually true. So if we were to do a couple of these terms by hand, again, I'm going to use like our polynomial expression up here. This would be just a 1 minus 1 cubed over 3 factorial plus 1 to the 5th over 5 factorial minus 1 over 7 factorial. We could go ahead and do that in our calculator. So 1 minus, I know that 3 factorial is 6, but I can also go under the math menu and under probability, and I could get my factorial symbol there. So that's 1 minus 3 factorial plus 1 divided by 5 factorial. Just have to go over each time. And then let's try one more term. So minus 1 over 7 factorial. All right, so we get this decimal 0.841468254, and if I type in the sine of 1, and we are in radians, well, the sine of 1 is pretty close to that. That's pretty accurate for the first 4 decimal places. So let's try this with more terms, and let's try this one in our calculator. So if we go under math, and we go to summation, we're going to start at 0. And let's try like the first 11 terms. So if I go from 0 to 10, that's really going to be 11 terms. So again, I would have a negative 1 to the power of x divided by 2x plus 1 factorial. So I need to go, oh no, I hit the wrong thing. Oh goodness. Okay, I paused the video to fix that. All right, so when we use the calculator, we notice that we are now getting, using just 11 terms of the series, we are now getting a decimal that is correct to at least 10 decimal places. What we're getting using the summation is the same as what the calculator is showing us for the sign of 1. Now, it's not going to be perfect because we only used 11 terms. And really, to make this a perfect, like an exact value for sine of 1, we would really have to use infinitely many terms here. So let's suppose that we are trying to evaluate the sine of -3. So the sine of -3, according to our series, well, I would still have -1 to the power of n, but this should be a -3 to the power of 2n plus 1 over 2n plus 1 factorial. So we could list out a few terms and calculate, but let's just go ahead using the summation feature in the calculator. So again, the newer operating systems have this. So if I go to math summation, so that's math 0, again, I want to start from x equals 0, and I can't go to infinity. That would be pretty cool. Let's say that we just do the first 6 terms. So from 0 to 5, that's 6 terms because x equals 0 is the first term there. And let's see, we're going to want to have a -1 to the power of x, since we can't do n, times a -3 to the power of 2x plus 1. And then all of that in parentheses divided by 2x plus 1 factorial. So again, math, probability, and it's number 4 there. All right, okay, so we get like -0.1408 and some change. And so if I actually type in the sign of -3 in my calculator, I see that like this approximation is okay. We're off by a little bit. So what if we just used some more terms? So instead of using like the first 6 terms from 0 to 5, I can just make this editable. Oh man. What if we went from 0 to 25? Well, all right, if you're trying this at home, hopefully your calculator is more agreeable than my on-screen calculator. Also, your computers, your school computers, at least the year that I am filming this video, have this Wabbit emulator, but you have the old operating system. So I can give you a file that would update yours to the new operating system. Just let me know for your school computer. Okay, so the first 26 terms. All right, well now I see that the approximation I'm getting in my calculator using the summation is the same as what the calculator is giving me for the sign of -3. Now again, if I go out, the sign of -3 is some irrational number, and if I go out like way, way, way further than the number of digits the calculator is showing me, these are probably, at some point, these numbers are going to diverge from each other. But for right now, this is like a pretty awesome approximation of the sign of -3. So in order to illustrate what we really want to talk about in this next lesson, let's look at one of the other series from last time. So let's look at our series 1 over 1 minus x. And we said that this is going to be equal, to x the power of n as n goes from 0 to infinity. So let's suppose that we want to know what we would get if x is equal to 1/2. So on the left, this would be 1 minus 1/2. And for our series, I'm just going to plug in a 1/2 for my x. Oops, that was supposed to be to the power of n. Well, I know that 1 minus 1/2 is 1/2, and 1 divided by 1/2 is really just 2. So I'm expecting to get an approximation that's close to 2 when I do this in the calculator. So let's see what happens. Let's say from 0, so I'm just going to go out to like, let's say maybe 0 to 10. So that's like our first 11 terms. And then I've got 1/2 to the power of x here. Okay, I can see that's pretty close to 2. I know if I approximate this with more terms, I'll get a number that's even closer to 2. But we want to see one more thing here. Let's try the same series here, but this time let's try this for when x is equal to 2. So if x is equal to 2, this would be 1 over 1 minus 2. And so I'm going to have a 2 to the power of n. And really, like the left side of this is a -1. And I'm expecting my series 2 to the power of n to work for this. So let's see if I can just go up and edit this one. So I'm just going to change my 1/2. Well, sometimes changing it is very slow. I'm going to change my 1/2 to a 2. All right, so this first like 11 terms from 0 to 10, this gives me 2047. That's kind of weird because that number is nowhere close to the number -1 that I was expecting to get. So we know that we could make more terms, like sometimes using more terms of our series will make our approximation more accurate, but I already know like something's fishy is happening here, right? This is very far off. Let's say if I go from 0 to 100. That number is huge. That's given to us in scientific notation, 2.535 times 10 to the power of 30. That's a really, really, really big number and nowhere close to the number 1. So here's what we really, really need to understand here. Sometimes our series and our function are equivalent for all values of x. But sometimes our series and our function are only equivalent for certain values of x. And so what we're going to talk about in this lesson is how do we find which values of x make the function in the series the same? And we're going to look at that graphically for just a moment. So on page 102, notice that this first graphic representation, notice that we have graphed the sine of x here. And we know the sine of x is going to oscillate between -1 and 1. So that kind of lighter graph is the sine of x. But laying on top of it, we have the first 20 terms of its series representation. So notice that for 20 terms in the middle here, one of these lies totally on top of the sine of x, but we could see that it's going to eventually diverge from the graph of the sine of x. But for those first 20 terms, those two graphs are indistinguishable from one another. And this happens for a certain interval of time before they diverge for one another. So of course, if we use more terms, we could get those to stay closer together for longer. So sine of x and its series representation are identical to one another. However, if we look at the graph of 1 over 1 minus x, we know that a graph like that is going to have some interesting behavior in the middle. So this is our graph of 1 over 1 minus x. When we graph the first 20 terms of the series that represents 1 over 1 minus x, we get this graph in the middle. And if we were to use more terms, it wouldn't get any better because our original function has an asymptote, and there is no way that we could get a polynomial function to look like a function with an asymptote. There's no way to get it to jump to the other side of that asymptote at x equals 1. So these two functions are only going to be equal to each other for certain x values. And notice these x values are from -1 to 1. And the reason is that this function is centered at 0, and you can only go 1 to the right because of the asymptote, so you can only go 1 to the left also. So these two functions, or this function and in this series, are only equivalent to each other for values between -1 and 1, whereas sine of x is equivalent to its series for all values. So this is called the interval of convergence. We're asking ourselves, on what interval does the series and the function match up perfectly? So if you plug in any number for x, you could plug the number in to the right-hand side to our series. If we go back to what we were looking at over here, if I plug in any number for x for sine of x, it will match up perfectly to the sine of that value. But down here, when we used x equals 1/2, this worked for us because 1/2 was on the interval of convergence. So 1/2 was between 1 and -1. Actually, that should be, it does not equal to. Whereas when we used our second approximation that we did, when we used x equals 2, 2 was outside of that interval of convergence. So, in short, our interval of convergence is the set of all x values for which the function and the series agree.